Okay, good morning. Hello, everybody. Mr. Tomashik here. Today, I want to talk to you about concentration. Now, at this point, you should know a little bit of vocabulary about solutions, things like solute and solvent. Solute, the stuff that gets dissolved. Solvent, the stuff doing the dissolving. Simple case, when you dissolve salt in water, salt is the solute and water is the solvent. And then you make a saltwater solution. Like that. All right, now concentration is how we measure how much stuff is being dissolved in a solution, and there's a number of different ways that we can do that, and we're going to consider a few of them. All right, first we're going to just call it a ratio of solute to solvent. Now, a lot of you are probably familiar with like a fish tank, or maybe even have a fish tank at your house, and there's a few things to consider when you set up a fish tank. Most people would have a freshwater fish tank, and what you have to do is first put water in the tank, and then you got to let it sit for a while before you add the fish, because most city water has a little bit of chlorine in it, and if you let it sit for a week or so, the chlorine will evaporate, and then you can put your fish in there. All right, now how much chlorine is in the water is what we call concentration, and you could measure it, and there's different ways that you could do that. Sometimes people have saltwater fish tanks, in which case you got to add salt to the water too as well, and you have to measure how much salt goes in there so that you can match, say, the ocean or wherever the fish came from. If you have a freshwater tank or any kind of fish tank, oftentimes you will see that they have a bubbler in there. You see these bubbles coming up? The reason for that is that makes oxygen dissolve into the water, and that's how the fish breathe. So that's a necessary thing for most fish. There are a few fish that don't need a lot of oxygen. But at the end of the year here, we're going to do a unit on water quality testing, and we'll come back and talk about that dissolved oxygen thing, which is a big deal for lakes, especially in Minnesota as well. So we'll be talking about that a little bit more later. But how much oxygen and how much chlorine or how much salt, that's all a matter of concentration. Now, there are a number of ways that we can measure concentration. We will consider a few of them. The first one is percent by mass, and there's a formula for that, and we'll give you these formulas right on the test as well. To calculate this, we will take the grams of the solute, the stuff being dissolved, divided by the grams of the solution, and then times 100 makes it a percent. Let's look at a couple examples. Determine the percent of by mass of sodium chloride in a solution made by dissolving 1.25 grams of sodium chloride into 100 milliliters of water. Now, we need the grams of the stuff. All right, now we got to realize that for water, 100 milliliters is going to be equal to 100 grams. Now, that's only true just for water, because 1 milliliter is 1 gram for water. All right, so here's how we'll do it. We'll take 1.25, the grams of the solute, divided by the grams of the solution. Now, the solution is going to be to add those two masses together. So we'll end up with a total mass of 101.25 grams of solution. And then divide times 100 turns it into a percent, 1.23%. So that would be a way to measure concentration, percent by mass, percent by mass. Let's look at another example. Determine the percent by mass of a solution by dissolving 0.01 moles of AgNO3, that's silver nitrate, into 50 milliliters of water. Now, we need grams and we have moles, so we'll have to go back to the periodic table and use the molar mass of AgNO3 to convert that into grams. And then we can do our percent by mass calculation. We'll take the 2.0 grams of the solute divided by 52. Now add the 2 grams together again, and then times 100 makes it a percent, 3.85%. All right, that is one way to measure concentration. The grams of the solute divided by the grams of the solution. Now, you could do it kilograms, but you'd have to have grams and kilograms of the solute and solution as well. All right. Another way to measure concentration is what we call parts per million. Parts per million. And for this, we will do grams of solute divided by grams of solution, just like we did before. But instead of times 100, we're going to do it times 1,000,000. That would be 10 to the 6. And we can abbreviate this as ppm, parts per million, parts per million. All right, if we're doing this times 1,000,000, whereas before we did it times 100, we could consider percents to be parts per 100, and that's exactly what it is. So the calculation is very similar. All right, let's do an example. Determine concentration in parts per million, ppm, when you have 1.25 grams of NaCl dissolved in 100 milliliters of water. Again, 100 grams, and we start the same way we did before, but instead times 1,000,000, or 1 with 6 zeros behind it. And then we will end up with parts per million, parts per million. Now, if we were following significant digits, we would have to round this to 3 significant digits, which would be 123 or 12,300 parts per million. We'll abbreviate that as ppm. All right, that's a different way to calculate concentration. A couple more examples. Calculate the concentration in parts per million. 0.012 moles of silver nitrate dissolved in 50 milliliters of water. Now again, we got to have grams to do this, so we'll need our periodic table and the molar mass and convert that into grams. And then we'll take the grams of solute divided by grams of the solution. Again, we'll add those two together times 1,000,000, and we get parts per million, parts per million. In this case, 38,000 parts per million. All right, let's try one more example on this. Air, which is 21% oxygen. If a cubic meter of air is found to have a mass of 1.2 kilograms, what's the mass of the oxygen part? Well, that's just a percent calculation. So I'll take 1.2 kilograms times 21%, and that will tell me how many kilograms of the air is of oxygen. How many kilograms of oxygen is in that air? All right, then we can do our parts per million calculation. All right, we'll have 0.252 kilograms and then 1.2 kilograms of the air times 1,000,000. All right, just remember that if the top's in kilograms, the bottom's got to be in kilograms as well. So we'll end up with 210,000 parts per million. All right, what kind of things do we measure in this parts per million? Now, carbon monoxide, which is a poisonous gas, is something that we'll often measure in parts per million. You can read that little paragraph there, but basically they're telling us that concentrations as much as 667 parts per million could be toxic to the human body. And anything above that would be kind of dangerous. All right, now OSHA is the Occupational Safety and Health Administration. They set standards for workplaces and schools and things like this, and they say that we should keep our concentration of carbon monoxide at 50 parts per million or less. All right, and that's pretty small. That's pretty small. Okay, a third way to measure concentration is what we call molarity. Molarity. All right, molarity is the moles of solute divided by liters of solution. Now, this particular way to do it is the most common way to do it in chemistry, and most of our calculations will probably involve doing calculations with molarity. And we'll even do some labs that involve this as well. All right, moles of solute divided by liters of solution. Let's look at an example. Determine the concentration in moles per liter when 1.25 grams of sodium chloride dissolved in 100 milliliters of water. The final volume is 103.2. Now, notice what happened here. This is similar to the last one, but if I start off with 100 milliliters water and I add 1.25 grams to it, its volume is going to increase. All right, its volume is going to increase. So that's something you got to take into account. All right, there's different ways to do this. All right, think about when you make Kool-Aid. If you get those little packets and you have to, make 2 quarts of Kool-Aid, if you start off with 2 quarts of water and then you add 1 cup of sugar to it, it's likely that the pitcher is going to overflow. So what you're supposed to do first is add the flavoring and the sugar and then add enough water to make 2 quarts. So it kind of depends on how you do it. So in this case, we end up with a little bit more than 100 milliliters because we added solute afterwards. All right, to calculate here now, we got to have our grams converted into moles. So again, we'll have to go back to the periodic table and look up the molar mass and calculate the number of moles. And then it will be moles divided by liters, and we'll end up with moles per liter. Moles per liter. Remember, to convert milliliters to liters, move the decimal 3 to the left. 0.1032. Moles per liter. Now, we could just leave it like that. And that would be fine. However, another way to write it, instead of moles per liter, we can write it as one big capital M. And that capital M means moles per liter. Just a different way to write it, moles per liter. We also call that molar. Another notation that we often see in chemistry is this. We got the formula for sodium chloride, NaCl, wrapped in a square brackets. The square brackets, in this case, means concentration measured in moles per liter. All right, we would read this as the concentration of sodium chloride is 0.207 molar, or moles per liter. All right, so that's what that square bracket indicates. We may see more on that thing a little bit later down the road. All right, so this is a more common way to measure concentrations in chemistry. Let's do a couple more examples. All right, how many moles is 2.3865 grams of CuCl2? That's copper 2 chloride. Now, this is just a convert to moles thing. You'll need the periodic table again for CuCl2. And now we can calculate moles per liter, or molarity. All right, number 2, we got that 2.3865 grams, and it dissolved it in enough water to give 500 milliliters. Now, notice how it says there, enough water to end up with 500. So don't start with 500 and add the stuff. You're going to add the stuff and then enough water till you get 500 milliliters of solution. All right, then we can calculate our concentration in moles per liter. Remember, 500 milliliters is going to be 0.5, move the decimal 3 to the left, and we'll end up with a solution that is 0.0355 molar, or moles per liter. That's the concentration. Now, question number 3. If I take that 500 milliliters of solution and split it into 3 beakers at the following volumes, what will be the concentration in each beaker? So I'm going to take that solution, split it up into 3 beakers, and I want to know what will the concentration be in each one of those beakers. All right, now realize that this is a trick question. All right, because we already know the concentration of it, and splitting it into 3 different beakers is not going to change the concentration of it. The concentration stays the same no matter how we divide it. All right, think of the Kool-Aid situation. If I make Kool-Aid, it has a certain concentration. All right, now some people like to add a little bit extra sugar, make it a little sweeter than normal. Some people a little bit less sugar on there, and how much sugar you add determines the concentration of it. And if I pour that Kool-Aid into 3 different glasses of different size, it still tastes exactly the same in each one because the concentration will not change by splitting. So don't be fooled by that particular question. You might see that one on the test. All right, let's look at a couple more. Number 4, how many moles of CuCl2 are in each beaker? Now, we have those 3 beakers here split up, and they all have the same concentration, but they each have a different volume or different number of liters. So if I take this formula, moles divided by liters, I can solve it for moles, doing a little bit of that algebra on the fly here. I'm going to take my molarity times the liters, and then I can calculate how many moles are in each beaker. Now the answer is different for each one of these beakers. All right, It's different for each one of these beakers. They all have the same concentration, 0.0355, but they all have a different volume or number of liters. All right? Therefore, we'll get a different number of moles for each one of them. Okay, question number 5. How many Cu2 plus and Cl1 minus ions are in each beaker? Now, realize when you dissolve something like copper chloride, CuCl2, it dissociates. It dissolves. The ions break apart and they just float around in the solution. For every one of those CuCl2s that I dissolve in the solution, I'll get 1 copper ion and 2 chloride ions in the solution. When they're dissolved as ions, you can't see them anymore. They sort of disappear. In the case of copper chloride, though, it does remain blue as well, but you can't see the stuff dissolved in there at all. All right. Now, if I wanted to figure out how many of each one of those ions are in there, in the case of the copper ions, I'm going to get exactly the same number as I got here for number 4, because for every 1 copper chloride that dissolves, I get 1 copper ion, so I get the same number. But I'll get exactly twice as many chloride ions as I do copper ions because of what the formula is. For every 1 copper, there's 2 chlorides. All right, so again, kind of a trick question, so don't be fooled by that. We'll do some practicing with this. All right, a couple more, and then we'll be done here. All right. If the water were to evaporate from each of those beakers, how many grams of copper chloride would be left? Now, if you took Kool-Aid and you evaporated it, what would be left in the glass? All right, you'd be left with sugar and flavoring in there. All the water would evaporate, but the sugar would still be in there at the bottom of the glass. All right, same thing here. If we evaporated each one of those beakers that we were talking about in the previous problem, we're going to get a certain number of grams in each one of the beakers. So we'll start with how many moles we have and multiply it times the molar mass, which is the same for each one. And it will tell us how many grams of copper chloride are left in each beaker after all the water has evaporated. All right, one last question. How many grams of copper chloride would be needed to make 600 milliliters of 0.2500 molar solution? All right, now I have that formula, molarity equals moles divided by liters. And what I need to find here, I know what my molarity is going to be, 0.25, that's the big M. And I know my liters, 0.6 liters. What I don't know is the moles. So I'm going to do a little bit of algebra here, solve that for moles, and I can calculate how many moles I get. Now, I need to know how many grams, so solving for X is going to give me the number of moles of the copper chloride, and then I'll need the molar mass to figure out the number of grams of copper chloride to actually make that amount of a 0.25 molar solution of copper chloride. All right, we'll do some more practicing of these kind of calculations too as well. All right, in fact, the next thing that I want you to do is do some sample molarity calculations with this DeWitt guy as well. All right, thanks for watching, and we'll see you later.